Welcome everyone, and thank you for joining us for our Headwaters Center speaker series. My name's Evie, and I am our Headwaters River Journey Manager, which just basically means I am in charge of our educational outreach. If you're unfamiliar with the Headwaters Center, we are a nonprofit in Winter Park that focuses on water conservation education. And thank you again for joining us today for a presentation by Dr. Ryan Smith. Ryan is from CSU, and he's currently leading the Remote Sensing Hydrology Group. His research focuses on integrating large-scale remote sensing and geophysical data sets to improve understanding of groundwater systems using process-based and machine learning models. Before Ryan came to Colorado, he was at Missouri University of Science and Technology, where he was working after he earned his PhD at Stanford University. So we will turn the floor over to Ryan, and thank you again for giving this presentation.
Great, yeah, thank you for the invitation. So before I start, I just wanted to say I'm happy to kind of let this go where people are interested. And so I've got a lot of slides, and if no one asks any questions, then I'll just go through my slides. But if you are really interested in a particular topic that I bring up, or even just somewhat interested and have some questions, feel free to chime in just throughout the presentation. And it always, I find that it tends to go really well when people do that. Okay, so yeah, so today I'm going to be talking about how we can get a better understanding of groundwater systems using satellite data and kind of coupling it with other more traditional data sets that we collect on groundwater. So to kind of preface the talk, I just want to talk about like the importance of groundwater globally. So surface water is something that we see all the time. We see rivers and lakes and streams. We don't see groundwater, but it stores the most liquid fresh water. It stores like 99% of liquid fresh water globally. And so as surface water supplies become more scarce due to climate change, and we're seeing that happen with the Colorado River and many other rivers across the US and globally, people are turning more to their groundwater supplies. In a lot of areas, there's still plenty of water in the ground. And you can think of it like a bank account. You can go into that bank account when you need it and pull water out of the ground. But the challenge is that even though we have a lot of water, there's many parts of the world and parts of the United States that are already depleting their groundwater resources pretty substantially, and we can expect that to get worse if it's not regulated as climate change again continues to stress our surface water supplies. So this is a map that just shows that across the globe, a lot of major aquifers that are under stress, and it glosses over a lot of smaller aquifers that are still significant. And I'm going to talk about some of those today. So one of the big challenges in managing groundwater is that across, and I'm going to focus this talk on the Western United States, but many of these issues apply across the world. But we don't know how much groundwater we're actually using in most parts of the country. So this figure shows on the top left, it shows where groundwater wells are being metered, so we know how much.
Hey, Ryan.
Yeah.
We can still only see your first slide.
Oh.
I don't know if you're on a different one at the moment.
Yeah, it wasn't a different one. Let me try sharing again. Thank you.
Okay.
Okay, are you seeing a different slide?
Yes, we are.
And let me just try advancing. Do you see a different slide now?
Yes, the satellite methods for estimating groundwater was the last one we just saw. Perfect. Okay. It is, just so you know, in presenter mode. I don't know a way around that.
Okay, I can switch it. I was seeing
perfect.
I was seeing it as not presenter mode. So I appreciate you letting me know.
No problem. Perfect. Okay. Thank you.
Thank you. And if that happens again, just let me know. Please. Okay, so yeah, across the Western US, there's a few states that have really good metering of their groundwater, and that Kansas is kind of the poster child. So and the reason they're metering so much water in part is that there's parts of their aquifer that have already been completely depleted and there's no water left. And there's other parts that are anticipated to be depleted within the next few decades. And so they've been really active at metering their groundwater use to make sure that people aren't using more than they're allotted to use. Colorado is also quite good at metering, but not the whole state is not metered, but a lot of the significant areas of pumping are. But many other states across the Western US, California is one that's quite notable. There's a lot of groundwater withdrawals in California, and there's very little metering and very little regulation historically. So one of the other big questions that we have with groundwater is how much can we sustainably use? And there's how much can we legally use, and that question it's a different question, and that's better known, I would say. But how much can we sustainably use is really not well known, in part because of the lack of metering data, and also just because of a lot of uncertainties that we have with groundwater data in general, just because again we can't see that. We don't. It's hard to know exactly where the groundwater is coming from and how much is coming from different regions. So the work that my group does is we try to use satellite data to better understand groundwater resources. And the idea is traditional groundwater monitoring is done with wells, and you drill a well, and that could cost anywhere from a few tens of thousands of dollars if it's quite shallow to several $100,000 if it's a deep well. And then you would monitor the water levels in that well over time. And that's an effective way of monitoring groundwater. The problem is you're only getting information at one location, and how does it vary as you move away from that location? And so that's where satellite data can really be helpful if we can understand how to link what we're seeing from satellites to groundwater processes. And that's what my research group is really interested in doing. So the satellite data set that we use the most is called Interferometric Synthetic Aperture Radar, and that's a mouthful, but InSAR is the short acronym. The general idea is that as groundwater moves throughout aquifers, you have changes in groundwater storage. As that occurs, if you have an increase in groundwater storage in your aquifer, that will cause the ground to uplift a little bit. And if you have a loss in groundwater storage, that will cause the aquifer to consolidate, and the ground will sink a little bit from that. And so in this, we're talking like millimeters to centimeters of displacement at the ground surface. And this is something that we can measure with InSAR. So the idea of InSAR is that you have a satellite radar. The satellite shoots the radar out, and it hits the ground surface and travels back up to the satellite. This radar has some wavelength. Usually it's on the order of 10 centimeters. So if you go back with the same satellite and make a repeat measurement, say a week later, 2 weeks later, and the ground has moved a little bit, then that wave will travel just a little bit farther or a little bit shorter of a distance. And when the wave returns to the satellite, we measure the phase, which is the position along the wave. And so minute changes in the ground surface that are sub-wavelength, so on the order of a centimeter, can be detected just by seeing if the wave traveled a little bit further, then there will be a change in phase. And I'll illustrate this in a figure here in this next slide. So here's our first satellite that takes an acquisition and creates an image, and this is the phase from that first image, and it looks completely noisy, right? It looks like there's no useful information in here. And that phase is just the position along the wave. And it's a function of like different scattering properties of all the different materials that are on the ground surface. So then you have a satellite that comes, typically the same satellite that comes back and makes another measurement at another date and produces a second image that also looks like complete noise. So now we have these two images, what we'll call our reference image, which is our first image, and that has some phase data, which again looks totally random. And that phase is just the position along the wave when that radar returns to the satellite. And we have something else called amplitude, which looks a little more like you can see that looks like there's some physical meaning in the amplitude. It's essentially just how strong of a reflection this radar produced, okay? But we're actually interested in the phase, not the amplitude, and I'll show you why in a second. So we collect our second image and it looks similar. So now if we take the phase from these two images that look totally random and we combine them and we take the difference between those, then we get something that looks like this. And this actually does have physical meaning. And I'm not going to go really deep into how InSAR works, but again, the main idea is that there are parts of this image that have deformed from one time to another, and the wave traveled just a little bit further. And so that change in phase, again, can give us centimeter scale accuracy in ground deformation. And that's a function of a number of things that I'm not going to get into right now, but suffice it to say that we can measure with centimeter scale accuracy ground deformation, and then we can relate that to changes in storage that are occurring in groundwater systems. So that's what my research group does, a lot of work with that, and I'm going to give some examples today on how we use that. But InSAR is not the only thing we use. There are many other remote sensing or satellite data sets that can give us some idea of groundwater systems and what's going on in those groundwater systems. We have to make some inferences to use them. But today I'm going to talk about two different topics. So the first one is going to be integrating a bunch of different remote sensing data sets to try to get a better estimate of groundwater withdrawals in regions that don't monitor that. And then the second topic will be really looking closely at some of the subsidence data. And I have a couple examples, one in California and one here in Colorado. Okay, so just to give you an overview of some of the other data sets that we can use, satellite data sets. I've already talked about InSAR. So this, it shows us how much the aquifer is compacting, and aquifers will compact more in regions that are really pressurized. So if you have an aquifer that is confined, those are typically deeper aquifers, and they have something that's blocking the water from moving up to the surface, and so the water can get really pressurized in those aquifers, and because of that pressure, if you start pumping, there's a huge loss in pressure, and that causes a lot of consolidation of materials. So because of that, we can see a lot of land surface deformation with InSAR. Another method, and I've got resolution here on the right-hand column, which is important to consider. So with InSAR, you can actually get better resolution than this, but with the free products that we typically use, we often are getting 50-meter resolution, and that's sufficient for most things that we do. If you want to get better, you actually can get better. Gravity is another method. So as we take water out of the ground, and really water, as water moves across the Earth's surface, even if it's not in the ground, if it's in lakes and things like that, or snowpack, that changes the mass of that part of the Earth. And we have satellites that are tracking the mass of the Earth by measuring gravity. So there's two satellites that are orbiting the Earth. And as they go over parts of the Earth that have higher mass, they get pulled a little bit closer to the Earth. And as they go over regions with less mass, they move a little bit further away from the Earth. And so it's pretty amazing, but you can use that to actually study how much water, how much water is changing, water storage is changing in different parts of the world. The challenge with that is it has to be a huge signal. So we're talking a 400-kilometer resolution. So like the state of Colorado or the state of California, that's what we could see changes in water storage at that scale, but not anything finer than that. So it's really interesting, but for water management, it's not as useful because the resolution is so coarse. Evapotranspiration is another really big one that I'm going to talk about. I'll continue talking about this in this presentation. So areas that use agriculture, that use irrigation for agriculture, use the most water, both surface water and groundwater across the United States. And mapping how much water they're using for agriculture is possible with remote sensing data. So we can map the greenness and the health of different plants to see how much water they're using. We can also look at temperature from satellite data, and if as evapotranspiration occurs, the air actually gets a little bit cooler above the plants that are using water, and we can use that with an energy balance to estimate how much evapotranspiration is occurring. And that has about 100-meter resolution. Again, if you want better, it's actually possible to get a little better with that as well. But suffice to say, at the field scale, so the scale of irrigated fields, we can map and measure with some uncertainty how much water is being used. And then you can estimate, like, is that water coming from groundwater sources or is it coming from surface water sources? There's other data sets here I'm not going to go into in too much detail, but land use is one other big one that with satellite data we can map out and see where there is irrigated agriculture, where there are urban regions, and we can get, if we have a good idea of like what the use type is, that can help us understand groundwater demand as well. So I talked about GRACE already. This is, and I didn't tell you what it stands for. The GRACE stands for the Gravity, Recovery, and Climate Experiment. And again, it's been really popular in the scientific community, but less useful for management because the scale is just so huge. And there are significant things happening, for example, in Colorado that we just can't see because the GRACE footprint has to be so large. This is another example, the High Plains Aquifer here. From GRACE data, it's shown to like not be losing significant amounts of water, but we know the southern part of the High Plains Aquifer is losing substantial amounts of water. It's just the resolution of GRACE, again, is not fine enough to constrain that. So in a typical study, if you wanted to understand the water budget and use that to understand like how much storage you're losing, you would just say like the change in storage, the inflows minus the outflows. It's a really simple idea. The challenge with groundwater systems is it's really hard to measure inflows, and then outflows as withdrawals, again, are unknown in many parts of the country. So the idea that we've had in our research group, and we've been doing a number of projects related to this for the past few years, is that if we can take these different satellite data sets and see that each of them is related to some component of the water balance. It's not an exact measurement, but it's some proxy for either inflows or outflows or change in storage in the groundwater system. And if we could somehow integrate those data sets, we could get a better understanding of these groundwater systems. But we don't have good models to do that. The other challenge is that each of these are available at different spatial and temporal resolutions. So we decided to use machine learning, and the idea is we have a bunch of data sets that we think are useful, but we don't know exactly how they relate to our variable of interest, which in this case is groundwater withdrawals. And so we use machine learning, and the idea of machine learning is you take some known data, so you go to an area where you have measurements of groundwater withdrawals, and then you let your machine learning algorithm learn the relationship between all these different satellite data sets, whether it's evapotranspiration, land use, precipitation, climate variables, soil moisture, all these things. We throw them into a model and let the model learn the relationships between all those input variables and our variable of interest, which is groundwater withdrawals. So we've done this in 3 areas. We've published papers in 3 areas where we've done this. We're continuing to do it in more areas as well. So Kansas, where we have the High Plains Aquifer, is one. The Mississippi Alluvial Aquifer in the Gulf region, the Gulf Coast region, is another one. This aquifer accounts for about 20% of the nation's groundwater pumping. So they're pumping a lot of water, but they don't know. So that's an estimate. They don't know exactly how much they're pumping. Because there's very little metering. And then Arizona was another region where there's some basins where the groundwater use is metered, but many basins where it's not. And so we used the data where it was metered to map out, to build a model to estimate with machine learning what the groundwater use was in unmetered regions. So this is the results from our Kansas study. You can see, and this is a good test case because we actually had the data for the whole state, so we could kind of test our model and see if it was working. So this is the actual groundwater pumping on the left-hand column, and then predicted pumping with our machine learning model on the right-hand column. And you can see that we're predicting the same spatial patterns, and we're also predicting the same or very similar magnitudes. And so this gave us a lot of confidence in that method for Kansas. We can use this machine learning model. We can look under the hood a little bit and see like what are the different variables that are really driving groundwater withdrawals. And we saw in Kansas, it was fairly easy to predict withdrawals just by where the irrigated lands are, and that's not unexpected. But this kind of helps quantify that relationship. And as in regions that had more evapotranspiration, we also saw pumping increased. As precipitation increased, there was less pumping because there was less demand for irrigated agriculture. So we use this model in Kansas to also forecast water use in different groundwater management districts. So this is GMD, or Groundwater Management District 5. This is Groundwater Management District 4, and it's showing the actual groundwater use that was measured compared with our model over different years, and it shows our predictions as well. So we can take climate data and say, well, given the current scenarios or future scenarios, this is how much groundwater demand we expect. And I mentioned that GRACE is not particularly useful for management, but if we took the entire state of Kansas and compared our withdrawal estimates with GRACE data, that's showing essentially the change in water storage, we saw some really similar trends. So periods where there was less pumping, you had an increase in water storage, and the opposite was also true. Okay, so changing gears now to the Mississippi alluvial plain in the Gulf Coast region. So again, there was very little groundwater metering in this area. This outline right here is in Mississippi. They call it the Mississippi Delta. And well, I don't know if you can see I'm gonna move my cursor over. Can you see my cursor here?
Yes, we can.
Okay, great. So this region, about 10% of irrigators were metering their water use, and then throughout the rest of this valley, there was no significant metering. And so the challenge here was to take those fields that were metering their water use and produce a model that would predict water use across the entire aquifer. Okay. So these are some of the variables that we used, and it was similar to our previous study, but we just had a lot less data here than we had in Kansas. But we were still able to produce a machine learning model that predicted water use, and it predicted it not just annually but monthly, which is what they wanted for their groundwater model. And it predicted it for different crop types. One thing that I think is important in these predictions is that we have some idea of what the uncertainty of our model is. And so we produced these error bars here as these vertical blue lines that show what our uncertainty is in each of our different monthly water use predictions. And this is just a comparison of our model with a previous model. There was very high uncertainty. Even in our model, we had an R squared of 0.52, which is pretty low, but it was significantly higher than their previous model. And one of the takeaways of this is that it's really hard to predict. So that this is our predictive accuracy at the field scale of how much each farmer is going to irrigate, given the climate and their crop type and their soil type. One of the takeaways from this is that it's really hard to predict what the individual irrigator's behavior will be, because each irrigator thinks about things differently. They may have a really wet year, and the irrigator says, well, even though it's a wet year, I still want to keep pumping just to make sure in case there's a dry period that comes, I want to keep the soil really saturated. Or you could have a dry year and the irrigator's like, well, I want to conserve my water and not use too much. And so there's just very different behaviors among different farmers. And predicting that is extremely challenging. But we were able to get pretty accurate estimates of the volume of water pumped across the region. And so this is the end result that we produced here on the right. And this was the initial model that the community was using prior to our study, which was basically a lookup table saying we'll take the crop type and we'll say it was a wet year or a dry year and then estimate based on those more simple factors. And so with the statistics we did, it looks like our model was able to provide a significant improvement over that, and extend these estimates of groundwater use. So again, why do we care about this groundwater use? You really need to know how much groundwater you're using in order to regulate it effectively, and to say if we know now how much we're using, then we can say this is how much we can sustainably use, because you can see years when you're using less water and there's no groundwater depletion, and so you can use that data to inform your management. But if you don't have that, then the management becomes extremely challenging. Okay, I'm going to give one more example or one more, I'll say, case study of this topic in Arizona. So Arizona is a very water scarce state, and they've actually been regulating their groundwater in some basins for quite some time. These basins that are outlined in orange have some amount of regulation, and they require all of their groundwater use to be metered. However, outside of those orange areas, there's no metering. And so this area down here, for instance, Southwest Arizona, we know there's irrigation there, but there's no metering. The same in this region right here, and some other regions in the southeastern part of the state. And so we, again, built a machine learning model that found the relationships between groundwater withdrawals and some of these same variables of interest in regions where we did have pumping data. And then we used that to build a model and predict withdrawals across the entire state. So the measured pumping is shown on the left, and our predicted pumping, where we filled in some of those gaps, is shown on the right. And if you just notice, like, why is there so many areas that have measured pumping on the left outside of the orange regions? Any area that says measured pumping that's in blue is basically, it's where there's no registered wells, and so we assumed that there was no pumping. So it's a quote unquote measured pumping of 0. Okay, so one thing that we found that was interesting in Arizona was that there were a number of basins, particularly outside of the management regions, that were having a dramatic increase in alfalfa acreage. So alfalfa is a very water intensive crop, and that was causing much higher groundwater withdrawal rates outside of the area where we had actual pumping data. And so we applied a correction factor to account for how land use was changing across Arizona. So kind of showing you all these 3 different regions. These were different studies that we put together for different collaborators and end users. So in one case it was the USGS, in one case it was the Kansas Geological Survey, and then here it was the Arizona Department of Water Resources. Oh, whoops. Yeah, well, I think I will advance to the next slide. So what we're doing now is trying to extend this work to the entire Western United States. And the idea is that we have some really useful data sets. We have ET measurements through a program called OpenET over the entire Western United States. And we also have estimates of where there are irrigated lands. So this is some work that a student of mine, Fahim, has been doing, where he took the evapotranspiration data and he clipped out all of the regions that are not irrigated. So now he's just showing you irrigated crop evapotranspiration. And we can use that to estimate crop water demand. Some of that water demand is being met by precipitation. And so Fahim's been working on estimating what we call effective precipitation. So if we think about when the rain falls over an area that's growing crops, not all of that water is going to the crop. So some of that water is going to enter the ground and infiltrate, and it will go into the aquifer system, and the crop won't have access to it. Some of that water is just going to run off and go into rivers and streams. And some of that water will go directly to the plant, and some will go into the soil that the roots are using, and the plant will use it. So Fahim's built another machine learning model that's predicting effective precipitation, which is what we define effective precipitation as the amount of precipitation that the plant is able to use. And what Fahim did was, I think, pretty clever. So he found areas that had grown rain-fed crops, so we knew that there was no irrigation, and he looked at those crops' water use, so their evapotranspiration, and that has to come completely from precipitation, from rain. And then he used that to train a model that predicted effective precipitation across the entire Western US. So that's what this is. So then once we have evapotranspiration and we have effective precipitation, we can subtract those from each other. We can subtract effective precipitation from evapotranspiration. And then we had an estimate of how much surface water is being used as well. And we subtracted that out. So using that simple water balance, we were able to come up with an estimate of groundwater withdrawals across the Western US. And this is preliminary. This hasn't been submitted to a paper yet, but it will be submitted soon. But we've compared these results with areas that are tracking their groundwater use across the Western US in Kansas, in Colorado. We've compared with groundwater use in Arizona and in Nevada. And the volumes of groundwater pumping that we're estimating are pretty similar to what has been measured. So we have a fairly high level of confidence in the accuracy of this method. Yeah, so anyways, stay tuned for that. That's an area that I'm really excited about. Okay, so I'm talking kind of slowly, but so I'm going to go through this section a little bit more quickly, unless there's questions and things, and I can stop and go and stay on topic for a little bit longer if there's interest. But I want to talk a little bit more about land subsidence. That's kind of how I open talking about InSAR and how we can monitor subsidence. So this is a really famous photograph, and I don't know how many of you have seen it. It's very famous in the groundwater community, I'll say. It's in the San Joaquin Valley in California, and it's showing that in this part of the valley, over a 50-year period, there was about 30 feet of land subsidence. So there's a massive amount of subsidence. So nowadays, there's actually very little subsidence that's happening in this area that had so much historic subsidence. So there's virtually no long-term subsidence happening over this area currently, but there is a lot of subsidence happening to the southeast of that location. So why has this area of subsidence changed? That's something this is a research question I've had for a number of years, since my PhD actually. So there's a few reasons why that could have happened. It could be that because it subsided so much historically, maybe the clays were just really compacted and they couldn't compact anymore. It could be that they just stopped pumping water in that area. And the third one is that maybe there's less subsidence in this area now because it's had a lot of historical stress, and the current stress it's under is not as high as it used to be. So that these aquifers actually have a memory. When they're compacting, they remember what happened to them before and what stress level they were under. And if they get to a higher level than they've previously experienced, then they collapse and there's massive subsidence. And if it's lower than what they've experienced before, then it's called elastic compaction, and it's usually much lower magnitude. So I'm going to just kind of briefly tell you how we went about answering this question. So we needed to build a model that would predict this subsidence in this region. We needed observations of subsidence, and we got that from InSAR and also from some historical leveling surveys. We needed estimates of water levels, or head, within clay layers, and those are the layers, they're so soft, and those are the layers that really compact the most. So we need to figure out what the head change was like in these clay layers, and that drives the pressure change, which is what drives consolidation. Then we needed some different parameters to run our model. So just at a really high level, this was the model that I developed for this study. We just had to solve all these equations. And so we came up with some computational methods to solve those equations and run this model. And this was our model. This was the model result for the two different regions that I was showing you. So let me just show you again. So region A is the area of historical subsidence, and region B is the area where there's a lot of current subsidence. Okay. So this is region A on top, and this is region B below. Oh, sorry. My cursor, you're not seeing my cursor. This is region A up top and region B below. And this is the head or the water level experienced in region A that had historical subsidence. So you can see the massive decline in head historically, and then it went up really high, and then it's been declining pretty substantially over the past few decades again. However, if you look at historical subsidence, there was huge historical subsidence, and then recently, even though there has been a decline in head, the subsidence has been much lower. And that just comes back, like I said, to the memory of this system. Even though we're losing head and declining in our water levels, we still haven't dropped very much below the historically lowest level. So we're not as stressed, as water stressed as we were historically. And that means that a lot of the consolidation is elastic. Whereas in this region, we're way below the historically high, the historically lowest water levels, which means that we're overstressed. We're more stressed than we have been historically. And that leads to this collapsing of sediments and this inelastic compaction. And that's why we have very significant subsidence in the recent past in that region. So hopefully I made that clear. I skipped over a few slides there, but that's kind of the takeaway about why. So we look at these different reasons why we could have subsidence or less subsidence in that region that had so much historically. It comes down to that, what we call the pre-consolidation head, which is the lowest head that's been historically experienced. That region had a very low pre-consolidation head because of their historical pumping. So I'm sorry I kind of went through that quickly. If there's questions, I can talk about that more. I wanted just at the very end to I'm gonna wrap up here in a few minutes, but I wanted to just talk about a few other areas where there's subsidence that we're looking at. So California has the most subsidence in the United States. I think this is a timed slide that's just advancing on its own. But there are other regions that we're also looking at that are interesting. And one thing that I'm really interested in is, why do some areas subside more than others? So you have a lot of groundwater pumping, for instance, in the High Plains Aquifer and the Mississippi Alluvial Aquifer, and there's no subsidence that's been detected. It's a very insignificant subsidence. There's quite a bit of pumping in parts of Utah that have caused significant subsidence, but still not as much as in California. And similar in Arizona and in Colorado, in the San Luis Valley, there is not as much pumping as there is in California because it's much more regulated. And I would say, even though they're quite water scarce in the San Luis Valley, but their regulation has been much better than in California. And because of that, there's much less subsidence, but there still is some, and we can use that to learn about the properties of the aquifer system. So there's a postdoctoral, let's see, there we go. There's a postdoctoral scholar in my group, Sanaz Vahedian, who is working on this in the San Luis Valley, and she's processed InSAR data in the San Luis Valley. And this is showing you subsidence from her data that she processed. So the blue is where the land is sinking, and it's over a 7-year period from 2015 to 2022. So south of the Rio Grande is where the main confined aquifer is in this valley, and that's where the head can drop the most, again, because it's so pressurized, even though there's actually less pumping in the southern part of the valley. So most of the pumping is happening up here, but there's higher magnitude subsidence down here because it's confined. And it just has to do with the physics of water, but they're losing more storage north of the Rio Grande, but more subsidence south of the Rio Grande. But if we look at a time series of deformation from InSAR, that's shown in blue, you can see every year in April or May, they start pumping and the land starts to sink. And then in October, well, let's say September, they turn off their pumps and the land rises again. And you see the same thing happens with their water levels. They turn on the pumps, the water levels drop. When they turn the pumps back off, the water levels rise. So these are just tracking each other really closely. The interesting thing that happened was in 2018, there was a huge drop in water levels. It was a drought year, and there was a larger than average subsidence. But then when the water levels rose back up again, the water levels rose back up to essentially what their previous levels were. So if you look to 2020, they've recovered back to what they were in 2017. But the ground surface did not. So there's a departure from the ground surface. It was tracking really well, and then it stops tracking as well after 2018. And that comes back to this idea of inelastic consolidation. So at this point in 2018, we stressed the aquifer more than it had been stressed previously, and that caused some collapse of the sediments. And it was still pretty small compared to California. It's just like a centimeter or so. Where in California, it's like 20 centimeters, but it was still enough that we could measure it with InSAR. And so we developed a model to simulate this. And the model it showed the same thing, that you had this inelastic consolidation that happened in 2018 from that large drop in water levels. So one of the takeaways from this is that by using this InSAR data, we can better understand the stress history of our aquifer systems. So just a quick example from the Parowan Valley in Utah. This is in southwest Utah. We did a similar study here where we were modeling to simulate so the black line is the model and the dots are the observed deformation from InSAR. And we're pretty happy with that model. And we modeled similarly some periods of inelastic deformation. But one thing I wanted to touch on before I close here is that by combining InSAR data with more traditional head measurements and withdrawal measurements, we can get a better understanding of how much storage the aquifer is losing. Because the aquifer is losing water from the sands, and that's where we're measuring our water levels typically, but it's also losing water from clays. And as the clays lose water, they compact, and we can measure that compaction with InSAR. So that in this Parowan Valley, we did a water balance, and we estimated in red the loss of storage from the sandy aquifer, which is typically the only thing that's accounted for when people do water balances. In purple, we showed what the water storage change was from the sands and the clay. So that's the total water that's being lost from our aquifer system. And it's about double what it would be if you just look at the sand. So those clays actually hold a lot of water, and they can lose a lot of water as they're being pumped from, or as they're draining into the sands. So that's an important thing to consider just with water balances, particularly in these confined aquifers. Just really quickly, before I close, this is something that we're working on in the San Luis Valley, and that we've also done in the Parowan Valley in Utah. We have this system that we can drive behind an ATV, and it maps out the subsurface material, whether it's sand or clay. And it can also give us an idea of where the water is in the subsurface. So it's nice, you can drive it behind an ATV, so you can cover a lot of area, and it gives you a much clearer picture of what's in the subsurface. These lines here are where we drove it, and it shows the data we collected, and it matches pretty closely to what the known lithology was in that area, and it will help also fill in some gaps where we didn't have known lithology. So just kind of wrapping things up, I hope I've shown you some examples. Well, I have shown you some examples. I hope I've convinced you that satellite data can be a really useful tool for understanding groundwater systems. And if you're a surface water person, I haven't really talked about surface water because I don't do as much research in that area, but it can be equally useful for mapping surface water. Snowpack. There's so many tools we have with satellite data to better understand our water resources in a time where water resources are becoming scarcer and scarcer and more important to manage. With that, I will close, and happy to take any questions if folks have some.
Hi, Ryan. I've got a couple of questions. I'm a groundwater lawyer in Colorado Springs, so this has been very interesting. My first question is to that third point on the slide there. I guess what I'm trying to understand is if, as these aquifers become more stressed and combined with that idea that they have this memory, as they compact, they're losing storage potential will they regain that storage potential, or is it just gone forever, or what happens, I guess?
Yeah, that's a great question. And like you were alluding to, it comes down to that memory that the aquifers have. So if it's elastic, then they can regain it. And so just as an example, in the San Luis Valley, in the summer, it's losing storage capacity, and then they turn off the pumps in the spring, and that storage capacity comes right back. And so that's your elastic deformation, which the San Luis Valley is mostly elastic. At this time, there's some inelastic deformation. So this, if you see like the blue line, the difference from here to here, that's the amount of storage capacity that was lost that we're not going to get back. And that occurs when you have this inelastic compaction, when it becomes more stress than it has been historically.
And that loss that we're seeing from 2018, 2019, I mean, is that going to take, thousands of years to recover from, or is that something that can recover from, through recharge? I guess just the lack of that loss in capacity. I'm curious what the timescales are.
Yeah, so there's two answers to that question. So the first answer is going to sound depressing, but it's not as depressing as it sounds. There is no recovering that lost storage capacity, so it's gone. The good news is we actually have plenty of storage capacity. So even though we've lost some amount of storage capacity, we're talking like a few centimeters of storage capacity in this example. In California, it's much worse. It's like tens of meters of storage capacity. But here it's just like a few centimeters. And there's like a lot more than that. That's a lot more storage capacity that's currently unused in the San Luis Valley, to take this example. And across the Western US, it's similar. So there is a lot of capacity to store water underground. It's not so much the storage capacity that's the issue, in my opinion, as it is just the trend. So if we're headed down, then we need to somehow do something to reverse that and start going back up. And if we do, then like I say, we have the capacity to store that water. We just have to find the water to put in there.
And one more question: do you guys have any plans to study the Denver Basin on the Front Range?
Yeah, so I'm interested in the Denver Basin. It's more it's like a consolidated system where you have these rocks that are less likely to form because they're consolidated. So I would expect the InSAR signal to be much smaller. At the same time, there are some shales in there that could be deforming, and I think it's worth looking at. I'm hoping to, but we don't have any funding to pay someone to process the data yet, and it's kind of a headache to get this data processed. So hopefully at some point we do.
Awesome. Thank you so much.
Yeah, thank you for the questions.
Question. So the InSAR, if I'm understanding correctly, it only goes, you can only detect 50 meters deep.
So the InSAR is detecting surface displacement. So it's just at the surface, but it's telling us about what's happening at greater depths. So it could be, and like most of the compaction in the aquifers that I've studied has occurred at depths from like 100 meters to 300 meters. But if it was happening deeper, then we would still see it at the surface. So as long as it's causing some surface deformation, it doesn't matter how deep it is. But like, I guess the short answer would be that most of what we see with InSAR is occurring from like 100 to 300 meters depth. That's what's causing the surface deformation.
But you can't exactly tell where in that 300 meters.
Correct.
Because what I'm asking is, like, are you able to tell which aquifer?
Yeah, that's
or how deep, or like, are you monitoring how deep these wells are and saying, okay, because they can vary in different places, right? So I just was wondering what the correlation was like. Are you seeing how deep these wells are, and then?
Yeah. So that's a really good question. And you're right. So InSAR itself does not tell you how deep. However, we've done a few different studies where we've had water level data. So you need water level data from different depths to disaggregate where it's happening. And if you have that, then you can do it. And so we've done a few studies where we have done that we've looked at water levels at different depths and then simulated the deformation from each of those depths and then summed it all together and then compared it to the InSAR signal. And from that, you can get a pretty good idea of like at what depths compaction is happening. So that's like the modeling approach. The more expensive approach is to drill a well and put in what's called an extensometer. And with extensometers, you can actually measure at a single point the compaction that's happening within a specific interval. And they've done that in Arizona and in California, but there's none in Colorado to my knowledge. Well, actually, Eric Harmon put in a couple kind of really rudimentary extensometers, but they're not there anymore in the San Luis Valley.
Interesting. Thank you.
Yeah, thank you. When you said 50 meters deep, it made me think of this. So that this geophysical system sees down 50 meters deep, but it's totally different from InSAR. So I just was going to mention that as well. And that's okay. One other just quick thought: if you use this system, you can map out where it's more clay rich, and that's at different depths, and that can give you an idea also of like where the subsidence is more likely to be sourced from.
I have a quick question. Could you talk a little bit about what the scale means for the like InSAR and GRACE? So when you say like 50 meters, what does that exactly mean?
Yeah, that's a good question. So that what I mean by that is that's the smallest area that could be resolved by that system. And when I say resolved, like you could see what's happening at that scale. So take for example, let's say that let's just say that we're trying to see where a house is, and the house is 30 meters by 30 meters. If you had a system that had a 30-meter resolution, then you could actually see the house. You wouldn't see the details of the house. You would just see that there is something there. But if you had something that was like a GRACE, that's a 400-kilometer resolution, you're not going to see a house. You're not going to see you'll see something that's happening across the entire state, but nothing smaller than that. I don't know if that helped answer that question or if it made it more confusing.
That helped. Thank you.
Okay, yeah.
All right. Do we have any more questions for Ryan at this time? It looks like that will be a no. Thank you so much for your presentation. I think we all found it very beneficial. Again, thanks for taking the time to tell us about your research, and thank you all for joining us, and keep your eye out for our next one. So thank you all.
Thanks for the invitation and thanks for the questions. Those were some great questions.
Have a good rest of your day, everyone.
Okay, bye.